In previous session, I explained electromagnetic waves, black body radiation, and photoelectric effect. In today's discourse, I shall explain photoelectric effect in detail, followed by atomic spectrum and Bohr's theory of hydrogen. In 1887, Heinrich Hertz performed a very interesting experiment in which electrons were ejected with certain metals like potassium, rubidium, cesium were exposed to a beam of light. The electrons travelled in the tube and a current was recorded. Thus, this effect is called photoelectric effect. On the basis of experiment, he observed that the electrons are ejected from the metal surface as soon as the beam of light strikes the surface. The number of electrons ejected is proportional to the intensity or brightness of light. No electrons were emitted when light below a certain threshold frequency or bombards the metal. The moment light crosses some frequency, the electrons are emitted. This frequency is called threshold frequency. All the above results could not be explained on the basis of laws of classical theory. According to classical theory, the kinetic energy of ejected electrons should depend on the intensity of light. This was not found to be true in experiments. Kinetic energy did not depend on the intensity of light used, whatever be the brightness of light. If it is below threshold frequency, electrons will not be emitted. Albert Einstein in 1905 explained photoelectric effect on the basis of Planck's quantum theory, according to which light is considered to be made up of small packets of energy, known as quanta of energy or radiation. Each quanta has energy equal to h nu, where h is the Planck's constant and has value 6.626 into 10 to the power minus 34 joule second, and nu is the frequency of light. Einstein explained the photoelectric effect. Thus, an electron absorbs a quantum of energy from light, and if the energy absorbed is greater than the minimum energy required by an electron to escape from the metal surface, then the electron is ejected from the metal surface with some kinetic energy. According to classical theory, the kinetic energy of electrons should depend on the intensity of light. The electromagnetic spectrum consists of radiation of different wavelength and frequency. An instrument used to separate the radiations of different wavelength is called a spectroscope. A spectroscope consists of a prism or diffraction grating for the dispersion of radiation and the photographic film to examine the emergent radiation with the human eye. And the branch of science dealing with the study of spectra is called spectroscopy. The spectra are mainly classified into emission spectrum and absorption spectrum. Emission spectrum may be obtained when the light coming after passing through a prism or a grating is examined directly with the spectroscope. Depending upon the source of radiation, emission spectrum are mainly of two types: continuous spectrum and line spectrum. When white light from any source is analyzed by passing through a prism, it is observed that it splits up into 7 different white bands of color. These colors are so continuous that each of them merges into the next. On passing through the prism, red color with the longest wavelength is deviated least, while violet color with shortest wavelength deviated the most. This is the example of continuous spectra, as there is hardly any sharp point that differentiate between colors or wavelengths. A line spectrum is obtained when the light emitting substance is in the atomic state. Therefore, it is also called atomic spectrum. Line spectrum can be observed against a dark or a faint continuous background. The characteristics line in atomic spectrum can be used in chemical analysis to identify unknown atoms, and in the same way as fingerprints are used to identify people. Absorption spectrum is observed when the light from a source emitting a continuous spectrum is first passed through an absorbing substance and then observed through an spectroscope. It will be found that certain colors are missing which leave dark lines or bands in their places. Such type of spectrum will be called absorption spectrum. The region of spectrum absorbed actually depends upon the nature of absorbing material. Absorption spectra is just like photonegative of emission spectra. The wavelength at which radiation is absorbed leaves a black line in the spectrum. Notice the colored lines. These are the wavelengths in which the substance has emitted the radiation after it absorbed the energy. This is the absorption spectra of sun. Notice black or dark lines in the different wavelengths. These are the absorption lines as the radiation from sun passes through its surface and it is absorbed at a particular wavelength. This is how we know about which elements are present, which are absorbed, etc., as each element has a typical absorption wavelength. Electromagnetic radiation is incident on matter. Then the particles gains energy and get excited to higher energy. When it comes back to the normal state, the particle has to emit energy. Every atom, when excited, emits radiation. These radiation form a line spectrum, which is the characteristics of the emitter. Each atom has its own particular line spectrum, which is regarded as the characteristics of the element to which the atom belongs. Like other elements, hydrogen has its own characteristics line spectrum. Hydrogen spectrum consists of a number of lines which can be classified into several series or several lines named after their discoverers. When a high voltage electrical discharge is passed through a sample of hydrogen gas at low pressure, hydrogen molecule dissociates and the excited hydrogen atom produced emit electromagnetic radiation of discrete frequencies. Unlike blackbody radiation, the color of light emitted by hydrogen atom does not depend on the temperature of the gas in the tube. When the emitted light is passed through a prism, only a few narrow lines of particular wavelength are observed, rather than a continuous range of wavelengths. The light emitted by hydrogen atom is red because of its four characteristics lines. The most line in its spectrum is in the red portion of the visible spectrum at 656 nanometer. In 1885, John Balmer showed that the frequencies of the lines observed in the visible region of the spectrum of hydrogen fit a simple equation. Wave number, that is nu bar, is equal to RH, that is Rydberg constant, into 1 by 2 square minus 1 by n square centimeter inverse, where n is equal to 3, 4, 5, 6 and so on. As a result, these lines are called Balmer series. The Swedish spectroscopist Johns Rydberg observed that all series of lines in the hydrogen spectrum could be explained by using equation wave number is equal to RH into 1 by n1 square minus 1 by n2 square centimeter inverse, that you can, where n1 is equal to 1 2 so on, n2 is equal to n1 plus 1 and n1 plus 2 and so on. The value 109677 centimeter inverse is called Rydberg constant and it is denoted as RH. For hydrogen, Rydberg formula explains the different energies of transition that occur between energy levels. The first 5 series of lines that correspond to N1 is equal to 1, 2, 3, 4, 5 are known as Lyman series, Balmer series, Paschen series, Brackett series and Piffin series respectively. Here you can see the spectral lines or spectral series of transition for hydrogen atom. Lyman series lies in ultraviolet region. Balmer series is observed in visible region. Paschen, Brackett and Piffin series are observed in infrared region. Only hydrogen atom has the simplest line spectrum. Line spectrum becomes more and more complex for heavier atoms. Niels Bohr explained the Bohrs theory. According to Niels Bohr, in an atom, electrons revolve round the nucleus in certain selected circular orbit. An electron is associated with a definite amount of energy in its selected orbit. And electrons are restricted to energy levels in which their angular momentum is an integral multiple of h by 2 pi. Energy is emitted or absorbed in quanta only when an electron jumps from one stationary state to another state. And when an electron jumps from a higher stationary state to lower state, a quantum of radiation is emitted. Further is the energy level from the nucleus, the greater is the energy of an electron. The energy of the electron in hydrogen atom has a negative sign for all possible orbits. This negative sign means that the energy of the electron in the atom is lower than the energy of the free electron at rest. When the electron is free from the influence of nucleus, the energy is assigned as 0. The electron in this situation is associated with the stationary state of principal quantum number n is equal to infinity. As the electrons get closer to the nucleus in the absolute value and more negative. The most negative energy value is given by n is equal to 1, which corresponds to the most stable orbit, and we call this the ground state. According to Bohr's theory, hydrogen atom, the stationary state for electron are numbered as n is equal to 1, 2, 3 and these are integral numbers are called principal quantum numbers. And the most important property associated with the electron is the energy of its stationary state. Niels Bohr undoubtedly made an improvement over Rutherford's nuclear model by providing the details about stability and line spectra of hydrogen atom and hydrogen-like ions. But it also lacked the following things. It is remarkably successful for one electron system but fails for many electron systems. He failed to explain the splitting of a spectral line in a magnetic field or electric field. He could not explain formation of chemical bonds. And the concept of electron moving around the nucleus in fixed orbit is not justified by Bohrs theory. That is all for today. In the next class, we will discuss quantum mechanical model of the atom. Thank you.